Today, we are going to talk about Euclidean geometry. Euclid may be considered the father of modern mathematics. About 300 BC, he wrote a book, Elements, where he laid down foundations of geometry and number theory. This book contained definitions, axioms, theorems, and rigorous proofs, and it was structured exactly in the same way as we do mathematics today. This approach is what makes mathematical knowledge rock solid. Unlike other sciences, where knowledge may be relative, say in medicine, what we believe to be true today may be refuted tomorrow. In mathematics, it is extremely rare that published theorems are retracted. Euclid's book, The Elements, was extremely influential and was used as a standard textbook up until the end of the 19th century. Today, we will be talking about vectors on Euclidean plane. Say we have 2 points, A and B, on a plane. One of Euclid's axioms for plane geometry states that given 2 distinct points on a plane, we can draw a line through these 2 points. And in particular, we can draw a line segment joining these 2 points. So let's give a definition. A vector that we will write AB is a directed line segment joining A and B. So here we take this line segment and assign a direction to it. Now, A here will be called the starting point of a vector, and B will be the end point. An important concept is equality of vectors. So let's give the definition. So 2 vectors, AB and CD, are equal if they lie on parallel lines have equal lengths and the same direction. So let us illustrate this definition. So here we have a vector AB, and someplace else we have a vector which is on a parallel line, CD, have the same length and the same direction. In this case, so if we join points AC and B and D respectively, then 2 parallel vectors will form a parallelogram. We define a vector as a directed line segment. However, there is a different mathematical interpretation of a vector. One can think of vectors as parallel shifts of a plane, or as we call it in mathematics, plane translations. So a plane translation is a transformation of a plane where we shift all points of a plane in the same direction. And then equal vectors will indicate displacement. So this vector can be interpreted that a point A moves to the point B, and the same vector or the same plane translation will move point C into the point D. Vectors are very important tools in physics, where they are interpreted not only as displacements, but also as velocities, accelerations, and forces. One important remark that we want to make about this diagram is that given a vector AB and any point C, we can always find a vector with a starting point at C which is equal to the vector AB. So this is clear from this geometric picture. So we can always draw a parallelogram using 3 points A, B, and C. And so then D will be the point that completes this parallelogram. Let us talk about operations on vectors. And we start with vector addition. So we want to add two vectors. Say we have one vector AB and say another vector PQ. Right. So how can we add these two vectors? There are, in fact, two equivalent ways of doing this. The first way is called head-to-tail rule. So what we do is we take the second vector, PQ, and find an equal vector with the starting point at B, at the endpoint of the first vector. And so basically we have to draw a vector on a parallel line, right? And this is, again, refers to one of Euclid's axioms that through a given point B, we can always draw a line parallel to the line PQ. And so then we draw this vector here, and so let's call this vector BC, right? So we have PQ is equal to BC. And then instead of adding AB and PQ, we'll be adding AB and BC. And the head-to-tail rule states that AB plus PQ is the same as AB plus BC and is equal to AC. So the sum of these two vectors, AB and BC, is equal to AC. Now, this is consistent with the displacement interpretation of vectors. So if we think that AB is the displacement from A to B, and BC is a displacement from B to C, then if we take a sequence of these two displacements, then we'll go from A to B and eventually to C. So the result of this sum, AB plus BC, will be the displacement AC. So this is a way how to understand the head-to-tail rule. The second equivalent way of adding two vectors is called the parallelogram rule. So in this case, so we take a vector, our second vector PQ, and instead of drawing it with the starting point at B, we will draw it with the starting point at A. So we have a vector AS. So we have AS, which is equal to the vector PQ. And now we've got two vectors with the same starting point. So what we do is we complete this picture to a parallelogram. So we draw a line which is parallel to AS through the point B. And we draw another line through the point S, which is parallel to AB. And here we get the point of the intersection C and the diagonal of the parallelogram is the sum of these two vectors. So what we have is, so we write that AB plus PQ. Now, because we said that PQ is the same as AS, so we have AB plus AS. And the result of this is the diagonal of the parallelogram AC. And if we compare these two pictures, then we will see that, in fact, the result, so this point C, is the same on both pictures. Because what we have here, so this vector AS will be equal to PQ, but it's also equal to the vector BC. Right? So because we have a parallelogram, so AS is equal to BC. Right? So these two vectors are opposite sides of a parallelogram, so they lie on parallel lines. And from properties of parallelogram, we also know that their lengths are equal. So these two rules are equivalent, and sometimes it's more convenient to use one rule, and sometimes it's more convenient to use another rule. When we talk about vector addition, it's important to remember that there is a very special vector, which is called the zero vector. So a zero vector is a vector that connects a point to itself. So it has the same starting point and the end point. And it doesn't matter which point we choose. So AA is equal to BB and is equal to CC, and so on. So basically, the zero vector represents zero displacement, and it's the only vector with zero length. We will denote the zero vector with 0 with a bar. And the zero vector has the following properties, that if we have any vector AB and we add the zero vector, then the result is still going to be the vector AB. So to see this, there are two ways of doing this. We can see this using head-to-tail rule, right? So if we use head-to-tail rule, then we need to write zero vector with the starting point at B. So this will be a vector BB. And using head-to-tail rule, so we go from A to B and then from B to B. So the result is AB. Or we can also use the parallelogram rule, right? So in this case, so AB plus 0 is the same as AB plus AA. And this will become a degenerate parallelogram, so the result will be still AB. Once we define a zero vector, it also raises the question about the opposite of a vector. So can we define the vector which is minus AB? And the property of a sum of a vector with its opposite must be equal to a zero vector. And it's clear that an opposite vector in this case is the vector which where the starting point and the end point will switch. And indeed, so if we use AB plus BA, so using head-to-tail rule, we see that the result is AA, which is a zero vector. So indeed, so what we see is that BA is the minus AB. There is a second operation on vectors that we will need. So this will be a multiplication of a vector by a real number. To illustrate this concept, let's consider AB plus AB. So how to add a vector to itself. So we have a vector AB, right? And then if we want to use head-to-tail rule, we need to extend this line and take another segment of the same length starting from the point B. So let's call this C, right? And so we'll have, so AB is equal to BC. And so then, using head to tail rule, so we'll have this AB plus BC, and the result will be AC. And this left-hand side is natural to call twice AB. And what we see is, so if we multiply a vector by 2, so we take, the result is a vector on the same line, but twice as long. So we can formulate the following rule. So to multiply a vector AB by a positive real number K, choose a point on a line, choose a point C on a line AB such that the distance between A and C over the distance between A and B is equal to K, and vectors AB and AC have the same direction. So in particular, so if we want to take something like 1/2 AB, then we need to multiply the length of AB by 1/2. So we're going to get a shorter vector here. So this vector here is 1/2 AB. So if K is negative, then all we have to do is we have to switch the direction, right? So for example, so if we want to have, say, negative 3/2 of AB, will be a vector that goes like this. And we point out that -1 times AB is the same as minus AB, and 0 times AB is going to be a 0 vector. In this course, we will often use these operations together. And so let's give an important definition. So let V1 through Vk be given vectors. And then vector C1 times V1 plus Ck times Vk is called a linear combination of V1 through Vk. And here C1 through Ck are real numbers. Let us introduce another definition of fundamental importance for this course. A basis of a plane is a pair of non-proportional vectors u and v. When we say non-proportional, we mean that neither vector is a scalar multiple of another one. And in particular, so this means that u and v are non-zero vector, because a zero vector is a scalar multiple of any vector. So if we multiply any vector by a zero scalar, then the result will be a zero vector. Because of this, when we say that two vectors are non-proportional, it also means that these two vectors are both non-zero. It is clear from the definition that a plane has many different bases, because we can choose pairs of non-proportional vectors on a plane in infinitely many different ways. Bases are important tools for computational problems. And in a given computational problem, we will choose a basis which is more convenient for solving that particular problem. Let's talk about the properties of a basis. So here we fix a basis uv. So let's make a picture. So we have a vector u and another vector v here. And the first property is that every vector w may be written as a linear combination of u and v. So this means that we can write w as c1 times u plus c2 times v for some scalars c1 and c2. Now, let us give a geometric proof of this fact. So we know that any vector w can be drawn with a given starting point. So let's think that our starting point here is O, and so then we can draw a vector w with the starting point. Say, suppose this is point C, so we can write that w is a vector OC. So then with this point C, we can draw a line through this point which is parallel to the line of a vector v, like this. And then we can also draw another line through the point C, which is parallel to the vector u. So in this way, we are going to get a parallelogram here. And so let us look at these two vectors on these lines of u and v. So here we know that two vectors on the same line are proportional. So let's give names to this point. So say this is a point A, and this is the point B. And so what we can say is that the vector OA is going to be a multiple, it's a scalar multiple of a vector u. So we can write it as C1 times u. And the point B, or rather the vector OB, is a scalar multiple of a vector v, because it's on the same line as the vector v. So we can write it as C2 times v. And by parallelogram rule, we have that OC, which is w, is equal to OA plus OB. So this is parallelogram rule. And so thus we get that the vector w is equal to C1u plus C2v. And so this geometric consideration shows that if we have a basis of two non-proportional vectors u and v, then any other vector on this plane can be written as a linear combination of the two basis vectors. Next, we make a simple but important observation about linear combinations of basis vectors. That so if C1 is not equal to 0 or C2 is not equal to 0, then the linear combination of basis vectors C1 times u plus C2 times v is not equal to the 0 vector. And this can be seen again from geometry, right? So how do we add, or how do we form a linear combination? So we have vectors u, v, and we take a multiple, so C1u here. And we take another multiple of v, C2v here. If C1 is not equal to 0, then the point C will belong to the line through the point A, which is parallel to the line OB. And for this reason, so this point C cannot be possibly equal to the point O. So what we see that if this happens, then so this vector OC cannot be possibly equal to the vector OO, which is the 0 vector, right? So simply because so this term C1u will produce a non-zero shift away from the point O, and then we are moving along a line which is parallel to the line OB. And so because these two lines are parallel and distinct, the point C cannot be possibly equal to the point O. As a consequence of this simple observation, we get the second important property of basis vectors. If a linear combination C1u plus C2v of basis vectors is equal to 0, to 0 vector, then both scalars C1 and C2 are equal to 0. And indeed, so this follows from the previous statement. So if one of these scalars were non-zero, then this linear combination will be non-zero. So the only way for this linear combination to make a 0 vector is to have both scalars C1 and C2 to be 0. We point out that this second property holds only for basis vectors. So if the vectors u and v are proportional to each other, then this property will fail. Or if we take more than two vectors, then this property will fail again. So, but if we have two non-proportional vectors on a plane, then this property will hold. Now, let us see how can we use vectors in order to solve problems in geometry. So let's do the following problem. Show that two medians in a triangle cut each other in proportion 2:1. Let's make a picture. So here we have a triangle ABC, and let's choose two medians. Suppose we have K, the midpoint of BC, and M, the midpoint of AC. And suppose P is the point of intersection of these two medians. So what we need to show is that the proportion AP to PK and the proportion BP to PM is 2:1. Now, in order to solve the problem, we choose a basis here. And the convenient basis would be to set vector U to be the vector AB and vector V to be the vector AC. So next, let us look at this property. This property says that any vector is a linear combination of basis vectors. Now, let's take a vector BC. And so what we want to do is we want to write the vector BC as a linear combination of U and V. How can we do this? So the trick is to decompose a vector BC into something related to AB and AC. And what we want to do is we want to use head-to-tail rule. And the trick is that instead of going directly from B to C, we are going to pass through the point A. So we're going to write BC as BA plus AC. And then we see that BA is negative of AB plus AC. And now what we've got is we've got our relation to basis vectors, because AB is U and AC is V. And so what we have is minus U plus V. So we were able to express the vector BC as a linear combination of the basis vectors U and V. Next, we want to do the same for other vectors that might be of interest to us in this picture. So let's do this for the vector AK. So how can we write AK? And again, the point is we're going to use head-to-tail rule. So to get from A to K, what we're going to do is we're going to go through B. So this is the same as AB plus BK. But what is BK? So K is a midpoint of BC. So this means that here we have AB plus 1/2 of BC. But for BC, we already got our expression. So here we have U plus 1/2 of BC. But BC is minus U plus V. And simplifying that expression, we get that AK is equal to 1/2 U plus 1/2 V. So here we managed to express the vector AK as a linear combination of our basis vectors U and V. Now, another vector that's of interest to us is the vector BM. So let's do the same calculation for the vector BM. So again, we use head to tail, and the convenient point to pass through is the point A. So BM is BA plus AM. Now, BA, so we need to relate this to U and V. So BA is negative AB. And what's AM? So AM, well, M is the midpoint of AC. So AM is just 1/2 of AC. And then the result will be negative u plus 1/2 v. All right, so I've saved the results of our preparatory work here. So let's go back to the problem that we need to solve. So what do we need to find here? So here we need to find the proportions in which the medians cut each other. So in other words, we need to find the ratios, say AP to AK, and we need to find the ratio of BP to BM. Now, let's call the first ratio X and the second ratio Y. Now, what we want to do is we want to translate this into vector equalities. So then this ratio tells us that the vector AP can be written as X times AK, right? So clearly, well, P was the point of intersection of the lines AK and BM. So this means that the vector AP is proportional to the vector AK, and the vector BP is a multiple of the vector BM. But because of these ratios of lengths, so what we get equalities for the vectors. So we get that BP is Y times BM. And we note that we already have calculated our vectors AK and BM. The next step is to relate vectors AP and BP through head-to-tail rule. So how can we do this? Well, one way of doing this is like this. We can write that AB plus BP is equal to AP. Right? So this is just a head-to-tail rule, but it involves both vectors AP and BP. And now what we're going to do is we're going to implement our idea. So we want to express everything as a linear combination of basis vectors. Well, for AB it's easy. So here we have just U plus. So what's BP? BP is Y times BM, and is equal to AP, which is X times AK. Now we substitute our expressions for AK and BM in terms of U and V. So we get U plus Y times, so what's BM? It's minus U plus 1/2 V. And this equals to X times AK, which is 1/2 U plus 1/2 V. So now let's collect everything on one side, and let's combine coefficients at U and at V separately. Now, so here we have 1U, so we put 1. And here we have negative Y. And from here we get, when we move this to the other side, we get X over 2 times U. And for V, the terms with V is going to be, so here we have Y over 2 times V. And when we move this to the other side, we get minus X over 2 V. And because there is nothing left in the right hand side, now we get that this is equal to the 0 vector. So we get this vector equation, right? So we get this multiple of U plus this multiple of V is equal to the 0 vector. But this is the time to invoke the second principle. So here we know that if a linear combination of two basis vectors is equal to a 0 vector, then both scalars in front must be 0. But that's exactly what we have here. So on the left, we have a linear combination of two basis vectors, right? Well, these scalars are a little bit complicated, but nonetheless, these are two real numbers here. And this linear combination is equal to the zero vector. So the only conclusion that we can make here is that both coefficients in front of our basis vectors must be zero. So from here, we conclude that 1 minus y minus x over 2 must be equal to 0, and y over 2 minus x over 2 must be equal to 0 as well. Now, we get, well, essentially a system of two equations with two unknowns. So here it's very easy to solve because the second equation just tells us that x must be equal to y. And when we put this in the first equation, then we get that 1 is equal to x plus x over 2, right? So because x is equal to y, then I substitute this y with x and I move it to the other side. And so what we get is we get 3/2 times x. And now we get the answer to our problem. Well, from the second equation, we see that x is equal to y. And from the first equation, we get that x is equal to 2/3. And so this tells us that so AP, so the length of AP is 2/3 of the length of AK, and that the length of BP is 2/3 of the length BM. And this means that the length of PK is 1/3 of AK, and the length of PM is 1/3 of BM. And so that tells us that these medians will indeed cut each other in proportion 2:1. This problem has the following famous corollary. That three medians of a triangle intersect at one point. So a priori, for three lines on a plane, there is no reason that they should have a common point of intersection. But for the three medians of a triangle, this is indeed the case. So let's make a picture. So if we draw the third median of a triangle, say CS, then so we're claiming that this median will go through the point P. So indeed, how do we show this? So we see, well, we ask the following question. How does CS cut median AK? And so now we apply our problem, but not to medians AK and BM, but to the pair of medians AK and CS. And so what we get is that so CS will cut the median AK in proportion 2:1, right? So the answer in proportion 2:1. So in the same proportion as the median BM cuts AK. And then this tells us that that CS also goes through the point P. Now this point P, the intersection of medians of a triangle, has important practical meaning. So this is the center of mass of a triangular plate. Imagine that we have a heavy triangular plate of concrete and we need to lift it. Where should we attach the hook to this plate so that it's easy to balance it as we lift it? And the answer is that this hook should be attached at the center of mass or at the point of intersection of the medians. Then it will be easier to maneuver this plate in order to properly install it. As an exercise, let's use vectors to solve another problem. So in the triangle ABC, let the point K divides BC in proportion 2 to 3, and let M divides AC in proportion 1 to 4. And let point P be the point of intersection of AK and BM. What we want to find is we want to find the ratio of AP to AK. Now, in order to solve this problem, we are going to introduce a basis. And as a basis, we choose vectors U, which is AB, and a vector V, which is AC. So the next step is we want to express all interesting vectors in terms of our basis vectors, in terms of U and V. And which vectors are interesting here? So this will be AK and BM. Well, before we do this, so let's start with the vector BC. Well, we can write that BC, using head-to-tail rule, we're going to pass through A, so this is BA plus AC. And so BA is negative AB. So this is negative U plus V. And now we can deal with AK. So AK is equal to AB plus, so because K divides BC in proportion 2 to 3, so this is going to be 2/5 of BC. And so that equals to, so AB is U plus 2/5 of BC, so minus U plus V. So that will be equal to, so U plus, or rather minus 2/5 U, so this will be 3/5 U plus 2/5 V. And we can write what is BM. BM is equal to BA plus AM. Now, this is equal to negative AB, and AM, so M divides AC in proportion 1 to 4, so this is 1/5 of AC. And so this is negative U plus 1/5 of V. Now, let's see, what do we need to find? So we need to find the ratio of AP to AK. Let's call this X. And it will be convenient for us to also introduce the second ratio of BP to BM and call it Y. Then these two equalities can be written as vector equations. So here we can write that AP is X times the vector AK, right? So because these vectors are on the same line, or we also say collinear, and BP is Y times BM. Now let us relate these two vectors, AP and BP, together using a head-to-tail rule. Well, so they're here. We have BP and AP. And here we can see that we can complete this to a triangle, ABP. And using this triangle, we can write a head-to-tail rule. We can write that AB plus BP is equal to AP. Now let us take these two equations into account. So we get AB plus BP is y times BM is equal to AP, which is x times AK. And next, we're going to express everything in terms of basis vectors using the expressions that we obtained here. So AB is just U plus y times BM. So this is negative U plus 1/5 of V. And that equals to x times AK, which is 3/5 of U plus 2/5 of V. Let us expand this and take everything to one side. So we have U minus y times U plus y over 5 times V minus 3/5 x times U minus 2/5 x times V. And since there is nothing left on the right hand side, this is equal to the 0 vector. Next, we combine all terms with U and all terms with V. So with U we get, so here we have 1 times U minus y times U and minus 3/5 times x times U. And with V we have this term here, y over 5 times V minus 2 over 5 x times V. All right, so at this point we use our second principle for the basis vectors. If a linear combination of basis vectors is equal to the 0 vector, then all coefficients of these linear combinations must be equal to 0. This allows us to equate the first bracket to 0 and the second bracket to 0. And we get 1 minus y minus 3/5 x is 0, and y over 5 minus 2/5 x is equal to 0. So we get these two equations. Now, from the second equation, easily, if we multiply this by 5 and move the term with x to the other side, we get that y is equal to 2x. And we can eliminate y from the first equation. So we get 1 minus 2x minus 3/5 x is equal to 0. And if we move it to the other side, we get 1 is equal to, so 2 is 10/5 and 3/5, so we get 13/5 over x, or x is equal to 5 over 13. And y, being 2x, is equal to 10 over 13. But basically, this gives us the answer, right? So what we had to find is we had to find the value of x here. And so this tells us that x is 5 over 13. And so this means that the point P divides AK in proportion 5 to 8. Right? So we have 5 parts here and 8 parts here. So altogether we have 13 parts, and AP is 5 over 13 times AK.
Thank you.